Hello Calc 3 and welcome back to another video. In this video we will be covering section 15.3 on area, or I should say calculating area by double integration. I will say that this video is going to be shorter than most, probably 15 minutes or less, so hopefully that's refreshing to hear. So let's get started. So in the previous section, section 15.1 and 15.2, we have interpreted the double integral geometrically as giving us the volume of a solid in three-dimensional space that's bound above by a particular surface represented by the function z equals f of xy. But in this section, we are going to talk about another geometric interpretation. So we're going to use the double integral to describe the area of a region inside of the plane. So we're moving from talking about solids in three-dimensional space to talking about regions in two-dimensional space and using the double integral to formulate an expression for the area of those regions. So let's move on here to areas of bounded regions in the plane. So if we take our function f of xy to be the constant function where f takes all of the points xy inside of its domain and sets them equal to 1, then the Riemann sums over some particular region R that we have in the plane are going to reduce to the sum from k equals 1 to n of the area of each of the k rectangles that are subdividing our region. So remember that we can draw a plane and we might have a region R inside of that plane that looks like this. And we can subdivide that region using lines that are going parallel to the x and y axis. And we're subdividing that region into a bunch of rectangles like the ones that are seen here. And we call that subdivision of our region a partition. And when we sum from k equals 1 to n, it means that our partition has n different rectangles that are contained inside of the region. So this is all review from section 15.2. And notice that then the Riemann sum is going to equal just the sum from k equals 1 to n of all of the areas of these small rectangles that are subdividing the region. But that means that as our partition, or as the norm of our partition is going to 0, and our small rectangles are covering more and more of our region R, then the sum of all of the areas of those small rectangles that are kind of checkerboarding the region, the sum of all of those areas is going to limit towards the area of the whole region itself. So we can say that as the norm of the partition goes to 0, then this sum from k equals 1 to n of the area of the k rectangles is approaching the area of our region R, the actual area, as opposed to the estimated area. And so we can move down to this definition here now of the area of a closed bounded plane region. And we say that that area is defined as the double integral of the function 1 over the region R. So we have this expression down here, where it looks the same as the double integral we had before, because it's the same as the double integral, but notice here that our function f of xy is assumed to be 1, because we're only concerned about the area here and not a volume under some surface in three-dimensional space. So it's probably best to solidify this idea by just going through a bunch of examples. So that's what I'll be doing for most of the rest of the video here. So for our first example, let's say we want to find the area of the region R that's bounded by the line y equals x and the parabola y equals x squared in the first quadrant. Okay, so the first thing we want to do, again, for these kind of questions is just sketch out what our region R actually looks like in the plane. So I have a sketch on the left here. We have our line y equals x in red and the parabola y equals x squared in green. And those two curves in the plane will intersect at the point 1, 1. And you can see that I have the region we're interested in colored in with purple. So we know that the area of that region is going to equal the double integral over the region R of the function 1. So, or you can just think about it as the double integral of dA over the region R. So we need to figure out how the limits of integration with respect to y and with respect to x, like we did in section 15.2. So I've decided to integrate with respect to y first in this case. And we can see that y is going to be bounded above over our region by the line y equals x, and it's going to be bounded below by the parabola y equals x squared. So that leads to these limits of integration over here. We're going from x squared to x, and we're integrating dy with respect to y, of course. And this leads us to the integral from 0 to 1 of y evaluated at x minus y evaluated at x squared dx. So we plug in an x for y and then subtract and what we get when we plug in x squared for y. So we end up with the integral from 0 to 1 of x minus x squared dx. And then we can take the antiderivative of x minus x squared. We get a 1/2 x squared minus a 1/3 x cubed. And again, we're evaluating from 0 to 1. And this will ultimately give us a 1/6. So the area of the region that we're interested in is equal to 1/6. And there is something interesting here to note. So if you just look at this expression here, this is identical to the expression that we would have used in Calc 1 to calculate the area of this region. So remember that if we have a region bounded above by a function and bounded below by a function, then the area between those two functions is going to be given by the integral from our lower x bound to our higher x bound of the top function minus the bottom function. And that's exactly what we get here. So we have the integral from 0 to 1 of our upper function x minus our lower function x squared dx. And so you can see that this new notion of area for regions in the plane using a double integral is just a generalization of what we had before from Calc 1 for calculating areas. The benefit of our new conception of area here, where we're using double integrals, is that this allows us to find the area of more general regions than we could have done in Calculus 1. Okay, so now on to the second example here. Let's say that we want to find the area of the region R that's enclosed by y equals x squared, a parabola, and the line y equals x plus 2. Well, again, like we always do, we're going to sketch the region R first. So I have the sketch over to the left. We have our line y equals x plus 2 in red, and we have our parabola y equals x squared in green. I also wrote down the points at which these two curves intersect in the plane. So on the left, we have the point -1, 1, and on the right, we have the point 2, 4. And again, we know that the area of this region is going to be the double integral of dA with respect to R, or over R. And so now we need to find our limits of integration. Again, I decided to integrate with respect to y first, just because it's a little bit less work, I think. So our lower limit for y is going to be where our vertical line enters this region if we're going up from the bottom. So notice that it enters at y equals x squared and leaves at y equals x plus 2 for all of these different values of x along here. So our lower limit of integration will be x squared, our upper limit of integration will be x plus 2, and then x is going to range from the point of intersection on the left to the point of intersection on the right. So we go from -1 on the left to 2 on the right. And so we end up with this iterated integral where we have the integral from -1 to 2 of the integral from x squared to x plus 2 dy dx. And now we can just evaluate this iterated integral. So we get the integral from -1 to 2 of y evaluated at from x squared to x plus 2 dx. We can plug in our x plus 2 for y and subtract what we get when we plug in x squared for y, and we get this x plus 2 minus x squared dx. We can take the antiderivative of x plus 2 minus x squared to get this 1/2 x squared plus 2x minus 1/3 x cubed. And again, we're evaluating from -1 to 2. So we take 2 and plug it into the expression, and then subtract what we get when we take -1 and plug it into the expression. and ultimately we get 9/2. And note again, we have the same phenomenon occurring here. So if we didn't want to use this, this new way to express area as a double integral, we could do this problem just using Calc 1, where we have the integral from the lower bound of x, which is -1, to the upper bound of x, which is 2, of our upper function minus our lower function, and that would work as well. But again, there are some regions where you will not be able to apply the methods from Calculus 1 directly, and I think the last example I have here will be one of those examples where we need this new notion of area that we just developed. Okay, so now I want to move on to another concept that we want to generalize from Calculus 1 to our multivariable functions now, and that concept will be average value. So remember in Calculus 1 that if we had a function f of x in one variable, then the average value of the function over some closed interval from a to b was given by the following expression, where we have 1 divided by b minus a multiplied by the integral from a to b of f of x dx. So intuitively, the way to think about this is you're taking the integral over the interval from a to b, and then you're dividing that result by the size of your interval. And that intuition is going to generalize over to the definition for average value for functions in two variables. So let's get down to that now. So here's our definition. The average value of some function in two variables, f of x, y, over a region R in the plane is given by 1 divided by the area of our region multiplied by the double integral of f of x, y, dA with respect to R. So hopefully you can see the similarities between our definition from Calc 1 and this new definition. This time we don't have an interval to take the size of. So if we have just an interval, then the size of the interval is going to be equal to the upper limit minus the lower limit, or the lower endpoint, I should say, of that interval. But when we have a region in the plane, the size of that region is going to be expressed by the area of the region. And so we just figured out how to find the area of arbitrary regions in the plane. And then we're going to multiply by the integral of our function f of x, y over the region R. So hopefully that makes sense to you now why this is a generalization of the definition we have from Calculus 1. And finally, the last thing for this video is just to give an example where we're finding the average value of some function. So we want to find the average value of a function f of xy is equal to x times cosine of xy over the rectangular region R, where x is between 0 and pi and y is between 0 and 1. Well, we could use the methods that we just developed to find the area of R, where we're taking the double integral of dA over the region R. But because R is just a rectangular region, it's just easier to use geometry to find the area. So the area of R is going to be the base times the height, or the width times the height, and that'll just be pi minus 0 for x here, and then 1 minus 0 for y. So we get that the area of our region R is equal to pi. And again, yeah, you could also calculate the area of that region R by evaluating this integral here, but who wants to do that if it's fine, if you already know what the area of that region is going to be just using some geometry. So then by definition, the average value of the function over that region is going to equal 1 divided by pi, because again, pi is the area of the region R, times the double integral of f of xy over the region R. And so we can represent that double integral as the iterated integral, where we have the integral from 0 to pi of the integral from 0 to 1 of x times cosine of xy dy dx. And notice here that we are integrating with respect to y first. And if we wanted to integrate with respect to x first, that would be significantly more difficult. The reason being that if we integrate with respect to x, then we have an x term here that's being multiplied by another function of x. If we integrate with respect to y first, then we can treat the x on the outside as a constant, and so we're really only integrating this cosine of xy and just treating that x on the outside as a constant, which seems much nicer, much easier to do. So we evaluate that inner integral from 0 to 1 of x times cosine xy dy. We get that the integral, again, we treat x like a constant, so that's just going to stay the same over here. But the integral of cosine of xy with respect to y is going to be equal to 1 divided by x times sine of xy. And now the x that's right here is going to cancel with the x that's right here. And so we get just this sine of xy evaluated from 0 to 1. So we take 1 and we plug it in for y, and that gives us a sine x. And if we would take 0 and plug it in for y, we get sine of 0, which is just 0. So it reduces to 1 divided by pi times the integral from 0 to pi of sine of x dx. Again, we take the antiderivative of sine of x and we get a negative cosine of x, and we evaluate from 0 to pi, and this will give us a 1 divided by pi times negative cosine of pi plus cosine of 0. Well, negative cosine of pi is 1 and cosine of 0 is 1, so ultimately we end up with 2 divided by pi. So 2 divided by pi is going to be the average value of our function f of xy equals x times cosine of xy over the rectangular region R, where x is between 0 and pi and y is between 0 and 1. And there should be some examples in the homework for you to practice this kind of idea. But that is all of the material for section 15.3. So again, this is a short video, and hopefully that's relieving to most of you. And section 15.4 will also be relatively short, I think, and that'll be up sometime tomorrow. So look out for that.